expect me to talk?
No, Mr. Bond, I expect you to die.
If you wanted to make 10,000 plastic models, you would most likely start off by making a mold and then letting machines inject molten plastic into the mold to shape your objects. But what if you just wanted one, a prototype so to say, that might still be changed later on? For just one, it's not worth the expensive process of making a mold, and that's where 3D printing comes in. CLIP, continuous liquid interface production, is one such technique and our topic today. CLIP is set up like this. A platform is submerged into a solution of monomer. A window below allows UV light to pass from a laser or screen into the solution. Where the light shines, the resin hardens, forming plastic that adheres to the platform, which grows a structure controlled by light. By letting a computer carefully control the UV exposure, a dynamic shape can be printed. Since one such print only takes a few hours, where making a mold may take weeks, rapid prototyping can be done, and that's where 3D printing excels. Now to the chemistry. Like in any polymerization process, in photopolymerization, monomers add together to form high molecular mass chains that yields a hardened material we call plastic. The difference here is that they're not initiated by high temperatures and unstable compounds, but are aided by light. Hence, the photoinitiators are much safer to store, such as benzophenone, a sunscreen derivative, against the more traditional AIBN that almost burned down a Japanese chemical plant. I'll be talking through the process of making polymethyl metaacrylate via photochemistry in the general context of CLIP. Step 1 is the photoinitiation via the very aptly named photoinitiator. As an example of a used type 1 initiator is alpha hydroxyl methyl benzoyl alkyl sulfonate, quite a mouthful. When exposed to the right frequency of UV light, it will absorb a photon. A short-lived excited state is formed that will rapidly break down either to reform the starting material or decompose into radicals by breaking a carbon-carbon bond. The radicals are the active species that initiate our polymerization process. K radical is the ratio between the concentration of the radical formed and the concentration of the excited state. In type 2 photoinitiators, the primary initiator requires the aid of a secondary compound to help it form its radicals. As an example here are benzophenone and diethylamine to aid it. Through a hydrogen donating complex, they form this hydroxy-substituted radical, which is much more active. The trade-off between the two types is that of a high K radical value against the much better optical absorption of type 2 initiators. Hence, they require less intense UV light. Once initiated, the polymerization process propagates by adding more and more monomer together. In our acrylate example, this might yield up to 100,000 relative molecular mass units. Generally, monomers are chosen which form stable radicals. In our acrylate example, the ester functional group helps stabilize the radical. But more examples might be that of aromatic or conjugated systems that spread out the unpaired electron. The radicals are incredibly sensitive to side reactions, and this brings us to the major obstacle of photopolymerization and one of the core ingredients to CLIP. As you might have noticed, our atmosphere contains oxygen. This can diffuse into the solution and react with the radicals. This in turn forms peroxy radicals that through hydrogen abstraction from solvent molecules form hydroperoxy terminated chains. If we investigate the activity of the radical polymer chains, we notice that the short chains are the most active, and hence their concentration based on the steady state assumption is very low. Long chains, due to the high mass, are quite inert. This leaves the medium chains with the highest ratio of abundance to activity, leading to them being the most susceptible to attack the oxygen. Since the medium length chains get attacked by the oxygen and the polymerization process is not finished, it leads to a soft and sticky finish on the material, and who wants that? However, Reducing oxygen can be done in a multitude of ways. Often, oxygen scavengers are employed. These molecules, like diphenyl isobenzofuran, react preferentially with oxygen over the radical. But this means enough scavenger has to be present to absorb all of the oxygen that will diffuse in through the entire polymerization process. On top of that, a quenching time must be allowed for before initiation may proceed to reduce the oxygen levels. Oxygen is excited from its ground or triplet state to a singlet state by a sensitizer compound. The triplet state is a diradical, and via a 95 kJ per mole transition to the singlet state, it pairs up the two electrons, which makes it completely inert to radicals. The oxygen scavenger compound will only react with single oxygen, so it should be safe to store. The kinetics of this reaction were studied via ultra-fast infrared spectroscopy, which is definitely as cool as it sounds, as the half-life of single oxygen in solution is far less than 1 millisecond. Future innovations may work on monomer compounds that are more inert towards oxygen, or multiple compounds such as photoinitiators that can be very effective scavengers too. Clip both needs and fights oxygen's properties. The window is actually permeable to oxygen, letting a small amount of it diffuse into the solution, which builds a concentration gradient away from the window. The submerged printing area is lowered until just above the window, where the oxygen present below the platform around the window prevents polymerization by quenching all of the radicals in the so-called dead zone. This means no polymers form on the window which would block the light. Instead, the polymerization only occurs on the printing platform. As the plastic begins to thicken, the platform is raised, extruding its shape. If we now change the UV pattern, the changed extrusion will give us dynamic shapes and finally our finished product. As a final word, the industry is adopting 3D printing techniques like clip very rapidly. Everyday objects like phone cases are already being made this way. So whether you're looking for academic prestige or fortune, this might be the next big thing.